All right, this is chapter 6, 6.4. We're going to talk about the Green's theorem. Okay, so we are talking about the line integral, how to compute the line integral if there is a vector field there. Okay, the vector field line integral of the vector field over a curve, right? So, so here is the Green theorem is an extension of the fundamental theorem of calculus, right? So in the fundamental theorem of calculus, you have f of x dx a to b. You calculate the antiderivative, and you plug in b minus f of a, right? So we're going to extend this same concept. So this is area under the curve, right? The area under the curve from A to B. So that's what the fundamental theorem of calculus, right? So if you extend that same concept, so it relates to the line integral over the closed plane curve. So there's a curve, but that curve has to be closed, means it has to, whatever starts, it has to end. So it should be closed. This is not a closed curve, right? Or this is not a closed curve. It has to be closed. Okay. The very interesting thing is this Green theorem, just like in the fundamental theorem of calculus, it doesn't depend on the path now. It doesn't depend on the path. It just depends on the initial points and end points, right? Now the thing is that here, when you calculate the line integral, what we're going to do is we're going to figure out the area, what is the area does that curve covers, right? So if it starts from here, it goes around, then this area, so it looks for that area. Okay, so let's see what is that theorem says. Okay, so if R is a simple connected, simply connected means this is the area, that's a simple connected, right? But if the line is passing through like that, that's not simply connected. So it has to be only goes like that. Okay, it has to be like that. Doesn't matter how it goes, but it has to be connected, but it's simply connected. So if it is not simply connected, means something like that. All right, if it is crosses goes like that's not simply connected. These are not simply connected. All right, so that kind of space, if you look at that, a simply connected region with a piecewise smooth curve. So if you have that curve, and then we counterclockwise, if it goes to counterclockwise, if your curve goes to counterclockwise, that's a positive. If it is a clockwise, you just have to multiply by negative, so make it counterclockwise. Okay, and if P and Q are the continuous partials, so this is a P, this is a Q over here. If you try to find the line integral of this one, instead of now looking at all the curves around or that lines around the path, so what we're going to do is we're going to figure out this partials. You subtract this partials, and then we're going to take over that surface, that area. All right, so that area, and that gives us the line integral. So that's the very big revolution on Green's theorem. Okay, so let's see, let's try one example. If you do an example, that's be more clear. Okay, so first what you're going to do is we look at this. This is your P, this is your Q. Q comes with the dy and P comes with the dx. Okay, so if I wanted to figure out what is the line integral, so what you're going to do is now this one is a path, is if you look at this path, this is 0 0 and goes to 3 0 and then 3 4 and then go back to, goes like that. This is the path. All right, goes this way, this is counterclockwise, and then this is 0 4 and then go back to 0 0. All right, so this is a rectangle, right? So how do I set up this one? So if I want to use a Green's theorem, so the line integral of y square dy or dx plus x square dy I can rewrite this one as some area. This R region is going to be your R, this rectangular region. And then we're going to figure out Q partial with respect to X minus partial P with respect to Y. And then we're going to do that dy dx or dx dy. This is like a rectangular, so we're going to use that, and dA, area. Okay. So let's figure out first what is partial derivative of Q with respect to X. So this is Q with respect to is just 2x. Partial derivative of P with respect to Y is 2y. So I can rewrite this one as 2x minus 2y and then dA, right? So dA, and then this is your R. So now let's figure out how do I calculate this area here. So if you look at the area, so I'm going to go from 0 to 3 for x, 0 to 3 for x, and 0 to 4 for y. It's a rectangle, right? So I can go 0 to 4 and 0 to 3. So 0 to 4 is y, so dy dx. And then I'm going to put that 2. So there's a 2 is a constant. Can I move it all the way out? So x minus y. Okay. So let's continue here with the different color here. I'm going to do a different color. So if I do that 2, 0 to 3, and then if I take the integral with respect to y, it's going to be xy minus y squared over 2, and I'm going to go from 0 to 4 and dx. Okay, and then that 2 is still outside, 0 to 3, and then I'm going to do, if I plug in 4, that's a 4x minus 16 over 2. 4 square is a 4 square over 2, and then minus, I think that whole thing is 0, right? This is 0, so that's just the dx. So let's write down that, simplify a little bit. So 2 is there, 0 to 3, that's a 4x minus 16 divided by that's 8, and then we're going to put dx there. Okay. Let's see, we have a little space here down, so I'm going to do it over down here. Let's go back to a different color, blue, or maybe let's see, this time brown. Okay, so I'm going to continue here, and that's line integral is equal to, that's a 2 times, if I take the integral, that's a 4x squared over 2 minus 8x, and I'm going to evaluate from 0 to 3, right? So that's a 2 is outside. So if I put 3 there, 3 times 3 is 9. So 4 times 9 over 2 minus 8 times 3. And then I think that whole thing is 0, right? So altogether, that's what? 2 times 36 over 2 minus 24, right? Now, if I calculate that correctly, that's just a 36. If I multiply by 2, and that's a 48, 2 times 24, and that gives me negative 12. So negative 12 is your line integral over that, this rectangular area. Okay. All right, I'll stop this one here.